So in section 5.5, we're going to define something called the dot product. The dot product is something, it's an operation you can do on vectors, and it has a lot of applications. So let me start with the definition. I've got two vectors, u and v. The dot product of the two vectors, well, you're going to start out with two vectors and end up with a scalar. It's going to be a times c plus b times d. There's no more magnitude and direction. You're just going to get a number out of the dot product. And since it's just a number, it's a scalar. We can also at the same time define the length of a vector squared is going to be the dot product of a vector with itself. V dot v. So a couple other definitions that maybe I want to throw out here. This is something that always bothered me. Now, Ahmad's favorite physics professor in the world is Dave Stoddard. Great guy over at the Orchard Ridge campus. Dave Stoddard. Yeah. So kudos to Dave here. Stoddard. Stoddard. I thought it was Stoddard. Physics. But something that I first encountered in physics really bothered me. This idea of a zero vector. Zero vector. It was like, well, really what that means is 0i plus 0j. Does that bother anyone else? Yeah, me too. There's no magnitude here, right? If you were to calculate the magnitude, there is none. But, I don't know, they call it the zero vector. All right, whatever. I'm not going to argue with years and centuries of mathematics tradition, but there's a zero vector. You could also write it as 0, 0. So, yeah, just my notation for vector. But let's actually calculate a couple dot products then. And the dot product is actually useful in helping you find the angle between two vectors. Let's start out with some simple ones. So a friendly one to begin with would be problem number 8. V is I plus j. W is negative I plus j. Oops, negative I plus j. You could write these as 1, comma 1. What would this one be? Negative 1, comma 1. So if I wanted the dot product between these two, v dot w, here's my a and b, c and d. It's going to be the product of the x components, so 1 times negative 1, plus product of the y components, 1 times 1. And you get a very uninspiring 0. That's just going to mean something for us later on. Right now it's just a calculation. Let's do one that doesn't necessarily come out to 0. That'd be problem number 10. V in this case is 2, comma 2. So 2, comma 2, or it's written in the book as 2i plus 2j. Likewise, W is 1, comma 2, or in the book, I plus 2j. So let's find V dot W, the dot product of these things. Well, can anyone tell me what to write for V dot W? What should I be multiplying? 2 times 1 plus 2 times 2. So 6 for the dot product between these two. So that's nice. It's a cute little trick. It's a mechanical calculation. But where can we use it? I mean, what's it good for? Well, let's keep an eye back on this here. That the length of the square of the length of a vector is given by a vector dotted with itself. And if we apply this kind of thing to the law of cosines, we actually get something kind of interesting. So let's do that. Or let's actually let the book do that. If you apply the law of cosines to this triangle right here, so it has sides of u and v, and this one is u minus v, then what do we get? Well, here's your law of cosines. If you write this out as u minus v times u minus v, and then these as u times u, or u dot u and v dot v, you get something like this. Kind of a mess. But then you start fiddling around with it, cleaning it up a little bit. You get down to something like this, and something nice happens. You can subtract that out from both sides of the equation. What else can you subtract out from both sides of the equation? The v dot v. That disappears. So you're not left with much, right? You're left with the minus 2u dot v, and this term over here, you can divide this by negative 2, and you're left with this. Finally, let's divide both sides of this equation by the product of these two magnitudes, or lengths, and you get this nice equation right here. And let me write that down for us, because this is a handy equation. It's a very mechanical way of finding the angle between two vectors. So let me write that down. The angle between two vectors, call them v and w, is given by cosine of theta equals u dot, or excuse me, I should be writing with v's, right? V dot w divided by the length of v times the length of w. And let me make that look more like a v here, so not to confuse things. V dot w. So that's pretty nice. Nice little formula that we can use here. And let's use it. Let's find the angle between two vectors. We'll start with problem number 12. In problem number 12, v is equal to I plus square root of 3 times j, and w is I minus j. In kind of our angle brackets notation, this would be a 1, which is your coefficient of I, and square root of 3, which is your coefficient of j. This would be 1 and negative 1. Let's do a bunch of calculations kind of all separately. So let's start with v dot w. What would v dot w equal? Be 1 times 1 plus, what else? Square root of 3 times negative 1. So basically 1 minus the square root of 3. There's two more things I need. I need the length of v and the length of w. So the length of v, okay, well, let's see. Length of v is going to be the square root of 1 squared plus square root of 3 squared. Of course, the mod already has that done. That's 2. Good job. Is anyone ahead of a mod on this next one? 1 squared plus negative 1 squared gives me the square root of 2. So I think I've got pretty much everything I need to fill in and work with this formula. By the way, that's one that you're going to have memorized. The interesting thing about this formula is that not only does it work in 2 dimensions, but it works in 3 dimensions, 4 dimensions, 5 dimensions, works in any dimension. So that's kind of cool. Considering that this works in like the 5th dimension and anything higher that we want, it's interesting that we can calculate the angle between vectors that we can't even see. So, wow. Talk about that with what's that? Because we prove it mathematically. So, the proof that I showed you is actually independent of the dimension of the vectors. It can work for any size vector. So what are we going to get here? Well, cosine of theta is going to equal v dot w, which is going to be 1 minus square root of 3, divided by the length of v, which is 2, times the length of w, which is the square root of 2. Now that's theta. How am I going to find, this is the cosine of theta. How am I going to find theta? Yeah, inverse cosine. Cosine inverse of 1 minus square root of 3 over 2 square roots of 2. Let's see if we can't make a little bit of a prediction before we actually calculate this out on our calculator. Now, it's not always going to be feasible to draw these things, but in this case, it's pretty gentle. And let me do the best I can without taking too much time. So let's start with W. W should be pretty easy, right? 1, negative 1. What quadrant is W in? 4th quadrant, right? So 4th quadrant, it's going to be someplace down here. 1, negative 1. Without doing any trig, can anyone tell me the angle here involved? Just the positive angle, not this way and not the negative. How much of an angle is this? Yeah, 45. That's the angle that I'm looking for. All right, it's true that it's 315 this way or negative 45, but let's just call it the 45. The other one is 1 and the square root of 3. So 1 and the square root of 3 is going to be up here. So here's the square root of 3. Here's your 1. This was a 2. We already calculated that. You might recognize this angle as well. That's your 60-degree angle. So between these two vectors, if I went from one vector to another, what's that distance? What's that total distance? What's the total angle between those two? 105. Let's compare that to what we get when we do the inverse cosine here. That one's kind of a pain. And for this, it's probably a really good idea if you have your calculator up to date so that you can do fractions the right way. Or not the right way, but a convenient way. So, well, that it has the latest operating system. Make sure your calculator's in Radian mode. I got in trouble in my calc class this morning because I had things in degree mode and the answer was wrong. So I want the cosine inverse. I hit the alpha key, then the y equals key so that you can make the first selection, press a 1. Alpha, and then the y equals key allows you to draw a fraction. 1 minus the square root. If you don't have this set up on your calculator, that's fine. Divided by 2 times the square root of 2. And it's just like I typed it in. It's in degree mode. Bam, 105. If you don't have your calculator set up this way to allow that, then let me give you an alternative. We're going to calculate this term inside in kind of pieces. So the first thing I'll do is I'll calculate 1 minus the square root of 3. Should give me negative 0.72 or 73 something. All right. Now I want to divide this by 2 square roots of 2. So hit the divide key and put parentheses here. Parenthesis 2 square root of 2. and then a closing parenthesis, just for good habit. This is the decimal value of this messy thing in here. If you do second cosine, that's the cosine inverse. I don't feel like typing that in again, so hit second and then this key down here, your previous answer. And I should get the same thing. So that's a different way to calculate it. It's up to you, whatever works for you. If your calculator is not up to date in terms of being able to do fractions like this, then it's not a bad idea to update it or borrow one of mine. No. Degree mode. Sorry. I said I was working in degrees for my calc class. I should have been, or working in radians, I should have been, no, working in degrees, should have been in radians. Did I? All right, my bad. Yeah. All right, you should be in degrees for this one. Yeah. Thank you. Thank you. Yeah. All right. So 105. And it matches. It matches what we looked at visually. Visually, we expected 105 degrees, and that's what we got when we did our calculation. So, okay.
No, for the first one, Jeff,
Yes.
45. Is that because, I mean, you figure it's 45 because 1 and 1 done there?
Yes, it's using Ahmad's theorem from the last section. They're equal, right? So that's a 45-degree angle.
Okay. I don't know why I'm
So.
obsessed with that.
Yeah, so I didn't do any fancy calculations, but yeah, that was our 45-degree angle. And you got that because these had equal length sides. Anything else on problem number 12? Methinks we should probably do another one like that. What do you think? Probably 14. Yeah, I know. Yeah, goodness. Problem 14. Let me just write the vectors like this. 3, -4. And 9, -12. 3, -4, and 9, -12. So there's a few things that we want. We're going to work in filling in this formula. Cosine of theta is u dot v over the length of u times the length of v. And I'm sorry, the last time I wrote this, I wrote it with v and w. Same formula. It's the dot product of the two vectors divided by the length of u times the length of v, or divided by the length of each of these. Okay, some people are gasping, so let me rewrite this again. Cosine of theta equals v dot w over the length of v times the length of w. They're the same formula. I just, out of habit, I wrote u and v as opposed to v and w. So the same formula. Start by calculating the dot product, v dot u. Calculate the length of v and the length of w. Put it all together and get a cosine. While you're working on that, I'll help you figure out the interpretation of your result. You should end up with kind of an interesting result here.
when you square it, it becomes positive.
Okay.
So that's where you're making mistakes.
Okay, thank you. That seems right. It seems crazy, but I don't know. Because it starts at
Three times 9 is what?
oh,
27.
seven.
Negative 4
Oh, we're
times.
adding, right? I'm lost.
Right. No,
I
no.
see.
It's negative 4 times negative 12 is 48.
Yeah. But we have to add those two.
Plus, yeah, plus
Not
27,
multiply.
so it's 97.
Oh, I forgot to put my little pause sign up there. Sorry. V dot W is going to be 3 times 9 plus negative 4 times negative 12. So 27 plus 48 is 75. The length of V, square root of 3 squared plus negative 4 squared. Square root of 25 is 5. And the length of W, 9 squared plus negative 12 squared is the square root of 225, which is 15. Let's put that all in here. Cosine of theta is going to be 75 divided by 5 times 15, which is 75 over 75. Cosine of theta is 1. So what's the angle between these two vectors? It's 0. The inverse cosine of 1 is 0. So, wow, that's weird. What's going on here? Well, let's take a look at this graphically. Graphically speaking, here's your 2 points. I can't easily draw vectors, but this is my attempt at it. So, here's the first one. Here's the second one. They're in the same direction. There's no angle between those two. In fact, if you look at them carefully, you kind of see that, right? What about this tells you that the angle should be 0? One of them is just a multiple of the other. If you take this times 3, you get this. So all you're doing is you're really stretching vector V to get vector W. You're just multiplying its length. You're increasing its magnitude, but you're not changing its direction. Its direction is the same thing as vector V. Cool. Very nice, very nice. All right. How are we looking on that one? Okay. There's one more thing we're going to do in this section, and we're going to go back to our handout for this. Let me describe it in terms of problem number 20. Give it to you in general terms first, and then we'll work on the actual specifics of the calculation. So, problem 20, let's call this vector right here. Let's call it vector V. So that's vector V, pointing out from the origin in the direction of the second quadrant. And then I've got another vector here called W. I'm going to decompose vector V into 2 parts. Let me kind of zoom in a little bit, make this a little bit clearer. Part 1 is going to be this vector over here. And part 2 It's going to be this vector here. So, well, I put them there. But let me help you understand what these are, or what's going on with this first. I'm decomposing this into two vectors. One that's considered parallel to vector W, and one that's perpendicular to that vector. So vector V1, let's see, is it V1 that's going to be parallel to W? Yes. So we'll call this V1. V1 is going to be parallel to W. So meaning it's pointing in the same direction, whether it's opposite or in the same direction. If it's scaled different, that's fine. But it's pointing along this line someplace. So that's V1. The other vector, V2, is going to be perpendicular to this. So we're breaking it up into two new vectors. Now if you add these vectors together, and Ahmad's old physics professor would like this. If you add these two vectors together, one way to do it is by completing the parallelogram for my yellow vectors and then drawing the diagonal. Well, that's where we came from. We're going to do this in reverse. We're going to figure out what two vectors can serve as kind of a basis for this vector. There's a couple formulas involved, and let me share them with you. To calculate V1, we're going to need to calculate, V1 is going to be some multiple of W. And I'm not going to try and derive this for us because I think we're getting a little bit late in the evening. We're all pretty tired, so let me share with you what V1 is. Alpha is. Alpha is going to be V dot W divided by the length of W squared.
W is the same as U, right?
Well, this is W right here. It's
Saying in the book it says U.
oh, does it say U? Okay, yeah. So W is the same as U in the book. To get V2 is pretty simpler. You're just going to take V and subtract off V1. And what's left is going to be your V2. Now this is actually written for problem number 20. So let's do this with the problems, with the numbers in problem number 20. Problem 20 gives you V is negative 3I plus 2J. And W is 2I plus J. Now I'll write that alternatively with our angled bracket notation. 2 comma 1 here, and then negative 3, negative 2 here. You can verify in your handout if that's what I've graphed. So take a look here. Here's your V, negative 3 and 2. So that's that point. And then here's your W, 2 and 1. So both those line up. Let's start by figuring out what V1 is. So V1 is just going to be the dot product of these two vectors, V dot W, divided by the length of W squared. What's V dot W? What numbers are going to have to put together to find the dot product there? Negative 3 times 2 plus 2 times 1. Now the length of W squared is just going to be the vector dotted with itself, or you could just say, all right, well, it's 2 squared plus 1 squared, and I don't have the square root because we're squaring it. It disappears. Negative 6 plus 2 is negative 4 over 5. So that's V1. Excuse me, that's alpha, sorry. So that's alpha, not V1 yet. This is alpha. V1 is alpha times V. So negative 4/5 times negative 3 comma 2. In this case, I am going to distribute. I'll get, let's see, where's that right? Am I doing this?
Just to confirm, it's alpha times
This should be a W? It's W, yeah, that looks better. Times W, thank you. I was looking at that going, wait a minute, that's going to be in the wrong quadrant. So negative 4/5 times 2 comma 1, which is going to be, let's see, negative 8/5 comma negative 4/5. If you prefer it in decimal value, that's negative 1.6 and negative 0.8. So that's V1. Let's see if that matches our graph. So if we look at our graph, this point is supposed to be negative 1.6 and negative 0.8. Looks pretty good. How about this point up here? That's going to be our V2. This is V1. Let's figure out what V2 is. V2 is just going to be the difference between V and V1. So V2 equals V minus V1. Negative 3 comma 2 minus negative 1.6 and negative 0.8. Minus a minus is a plus. So that's going to become negative 1.4, and minus a minus is a plus, so that's going to be 2.8. How does that match up to our drawings here? Well, it should match up pretty good. So here's your V2. And these numbers would be negative 1.4, comma 2.8. And then likewise, down here we have, what was it? Negative 1.6 and negative 0.8. Basically, you've torn apart this vector V into two parts. One that's parallel to W and one that's perpendicular to W. And that was our goal. If
we want to find the angle between V and W, all we have to do is analyze V to be V1 and V2, and V1 basically is going to be parallel to W, and the second one would be perpendicular to W.
the angle between these should be 0 or 180,
Okay.
always. So there's two choices. It can point in the same direction or it can point opposite. So the angle is going to be 0 or 180. The angle between W and V2 should be 90 degrees. And I do want to make a comment about that angle. There's a special angle there involved. But to recap, this is just kind of a calculation. Alpha is the dot product of these two divided by the length of length of W. You scale W by multiplying it by that scalar. That gives you vector v1. Vector v2 is just the difference between v and v1. Okay. I did want to make one more comment relative to this formula right here, and that is the numerator. We ran into this the very, very first problem that we did. It was kind of a special case of this. I didn't say anything about it then. I do want to say something about it now. So that special case happened when we got a dot product of 0. So suppose that you've got two vectors and the dot product is 0. Let me write that cosine formula again. Cosine of theta is u dot v over the length of u times the length of v. And I'm sorry I didn't do it with w and v. Sorry. It's not going to change the result. Suppose this dot product is 0. If I get the cosine of theta is 0, does it really matter what the length of u and the length of v are if the numerator is 0? No, you're just going to get cosine of theta equals 0. Well, that's special. What angle has a cosine of 0? 90. Yeah. The inverse cosine of 0 is 90. So a very, very easy way to check if two vectors are perpendicular is to see if their dot product is 0. And just kind of like this formula in general, that's true in any dimension. So if you have the dot product of these two vectors and you get 0, then those two vectors are perpendicular. So that's cool. That's a nice, it's a very handy result. If u dot v equals 0, then u and v are perpendicular. Now, perpendicular is a term that we use in 2 dimensions quite often, maybe 3 dimensions as well. But like I said several times, this formula works for lots of higher dimensions. And there's a fancy word that you can use here if you want to impress your friends. It's orthogonal. Ooh, ah. Yeah, it's not something that comes up in the casual conversation unless you hang around with a bunch of nerds. So, or do CAD, yeah. Do you use it in like your CADs, your CNC?
You asking me? I had
Yeah.
An internship with a crane and rigging company.
Okay. Okay, so they used orthogonal?
Yeah, they had AutoCAD.
Okay, it makes sense. Right. So, did you like do a double take the first time they used orthogonal, or had you heard it by then?
It was the first time I heard about it, so it was pretty cool.
All right, cool.
That's the same thing as perpendicular.
Orthogonal and perpendicular, they're used pretty much interchangeably. In my mind, and I could be off on this, but in my mind, I use that when I'm talking about things that are higher dimensions. 2 dimensions, maybe 3 dimensions, I'll use perpendicular. Beyond that, in dimensions that we can't see, I'll just use orthogonal. But for practical purposes, they are perpendicular. That brings up a lot of cool things. I mean, talk about a cone of future uncertainty, stuff that you would see if you start working with Einstein's stuff, but we're not going to go there. Let's keep it friendly here. Okay. Let's see. Einstein. Yeah. What was I thinking? Sorry, I'm drinking the cheap stuff, man. Let's see. There was one last problem that I wanted to do here. It's a little bit more practice with this. It goes back to our previous section. I'm kind of surprised that they asked problem 78 in the previous section. It's problem 78 from section 5.4. And they want you to find the actual speed of an aircraft here. Now what's going on is that you've got an aircraft which is traveling west at 500 miles an hour, and you got the jet stream is blowing at 100 miles an hour in a southeasterly direction. So we want to find the actual velocity of the plane and the direction that it's heading. So part of it is something you could have done in the last section, but we are going to finish it up here. We're also going to take advantage of this formula. I think it's going to make the calculation a little bit easier, even though the numbers will be a little bit scary. Let me draw this for us. So this is problem number 78 from section 5.4. What angle is due north? It's actually 0 degrees. So due north is 0 degrees. Actually, more trivia. When you land in Metro Airport, if you're landing in runway 220, well, really take that, or runway 22, if you multiply by 10, you get 220 degrees. So it's 220 degrees from north is where you'd be landing. 90 degrees would be due east. 180 degrees is due south. So 220 degrees is a little bit west of due south. So south, of course, would be 180. If we're traveling at 500 miles an hour west, that means we got a vector that's pointing us to here. So this distance is 500. I could write that vector as negative 500, comma 0. The wind is blowing at 100 miles an hour this direction. 100 miles an hour southeast. So that one right there. So it's going to be 100 times this vector. Square root of 2 over 2 and negative square root of 2 over 2. If I add those two vectors together, then I can get the resultant vector. That is my actual heading, and then I can calculate the speed here. Let me distribute that and get 50 square roots of 2 and negative 50 square roots of 2. Please.
Could we look at the question again?
Sure. That's all right. So let's look back at the question real quick here. So we've got a plane that's traveling 500 miles an hour due west, and the jet stream, or the air, or the wind, is blowing 100 miles an hour in a southeasterly direction. So let me give these vectors some names then. Call that vector v sub p, and what, vector v sub a? The air, or the wind. Let's use A for the air. What's going to happen when we add those things together? Well, okay. The resultant vector here is going to have to be something a little bit south and a lot west. So I should get something kind of over this direction. So we'll call that the ground speed, how you're actually traveling relative to the ground. And it's just going to be the sum of these two vectors. It's going to be negative 500 plus 50 square roots of 2, and then 0 plus negative 50 square roots of 2. And that's your ground, that's your new vector. That's how you're actually heading relative to the ground. And one thing I could ask then is, well, how fast are you traveling? What's the net result of these two vectors? In other words, what's your speed? And your speed is going to be the length of that vector. Length of v sub g. This is where it gets a little bit ugly. Can you see that? That's your A, and that's your B. There's a lot of ugly out there. Yes. Please.
So you have 100 and then square root 2 of 2 comma square.
Yeah, I kind of.
Yeah, where did that come from?
All right, it's a good question. If you're traveling in a 45-degree angle, which was directly southeast, then this direction, say A, and this direction B, and I regret using A and B here, but then the cosine of, well, let's do cosine of 45 degrees is going to be the opposite, or it's going to be the adjacent over the hypotenuse. So it's going to be A over 100 is going to be your adjacent over the hypotenuse. What do I have to do to solve for A? Multiply both sides by 100. So I get 100 times the cosine of 45 as being A. Cosine of 45 is going to be square root of 2 over 2. So that's where I get A. Likewise, if you did 100 times the cosine, or excuse me, 100 times the sine of 45, I'm going to get the vertical direction, and I'll also end up with square root of 2 over 2. But what you have to keep in mind is you're in the fourth quadrant. So you get negative square root of 2 over 2. Derek, does that answer your question? Okay. And I distributed the 100 to get these two. The length of this is just going to be this squared plus this squared. So the length of this will be the square root of negative 500 plus 50 square roots of 2 squared plus negative 50 square roots of 2 squared. And that's just, it's ugly. It's just ugly.
We're not gonna get one of these on our.
It's possible.
Okay, so yes.
Yeah. We'll see. We'll see. I haven't written my exam yet. I'll write it sometime after
It's the holiday.
Saturday, if you know what I mean. Okay. Let's see what that looks like. No. We just need to calculate that value. So, parentheses, negative 500 plus 50 times the square root of 2. Square root of 2 plus, I can leave out the 50 there, or the negative 50 times the square root of 2. And yeah, I am going to need to calculate the square root of this when it's all done. The fast way to calculate the square root is raise that to the 0.5 power. So 435 miles per hour. So the wind blowing in the southeast direction like that is slowing you down considerably. If you've ever traveled from, say, Detroit to someplace in the west, it's always faster coming back home because you've got a tailwind. You've got the jet stream pushing your plane as opposed to fighting it. So, yes, 435.07, etc.
Is it wrong to just cancel the square with the square root?
Yes, that'd be wrong. All right, so that's the magnitude. If you wanted to find the direction, you could use this formula. Cosine of theta is the dot product of those two angles, of those two vectors. So you've got our new resultant vector here, be VG dotted with VP over the length of VG times the length of VP. Two of these we already know. We just calculated this. That's 435.07 the length of this, I don't think we really need to calculate that. Can anyone tell me what's the magnitude of this? 500. So that times 500. I really wonder what the author exactly wanted you to do without this formula. How would you do this in section 5.4 without knowing this formula? Not sure. The last part of it is the dot product here. So the dot product is going to be the dot product between this vector right here and this vector right here. The nice thing about this is that the dot product is going to include a 0, right? You can have this times this plus 0 times this. So, all right, we get kind of lucky there. Really what it works down to is negative 500 times this, negative 500 plus 50 square roots of 2. And the rest of it is just a 0. Let me come up with a decimal value there, and then we can finish this off and then take a break. What's that? You know, you can. Negative 500 times negative 500 plus 50 square roots of 2. Divided by, now let's come up with the numerator first. Did I say? Yeah. So 214,000 and change divided by these two. 435 times 500. Hopefully this gives me a value less than 1. It does. If you take the inverse cosine of that answer, we've got the angle between these two things. So, made about a 9-degree difference to your flight. Over the distance of, hundreds or thousands of miles, that's going to be a big deal. You don't want to be off by that much. So you're going to have to do a course correction. Whew. For homework. Now we worked hard in this section, so let me give you an easier time of the homework. Well, what we ended up with was 9.35 degrees. So that's the difference in our course. If you project that over however far you want, I mean, it's going to make a substantial difference. So over the distance of, say, 2,000 miles, so let's see, the sine of that angle, let's see, let's do the cosine, let's do the sine of that angle. Sine of 9.35 times, say, I don't know, roughly 1,500 miles from here to Phoenix. That's 243 miles off. Yeah, it wouldn't even be close. All right. You'd still be away. What's that? No, you'd be closer to Flagstaff, assuming that you were north. Which, Flagstaff's a cool town, but good luck landing in the mountains there. Okay, for homework. Section 5.5. Try problems 7 through 20. We'll do 22. No, 21. So homework 7 through 21. That's pretty merciful compared to some of the hard work we did here. Cool. No.